XYK model is dual to something complicated that we don't understand in detail, while a simple bulk system, namely this, is dual to an average of quantum systems, not to a specific bona fide quantum system. So this sentence is a piece of what Steve Shenker explained this morning, and I think it's quite interesting. So it's actually what fascinates me about the topic. But unfortunately, I don't have anything to tell you that continues this line of thought. What I have to offer are only technical extensions of what you heard about this morning. So a simple correspondence of JT gravity with a random matrix is possible in part because JT gravity is very simple. So, as Steve in part explained, part of the simplicity is that JT gravity is one loop exact. And that's because if you take this integral and integrate over phi, you'll get a delta function saying that r plus 2 is 0. In other words, you localize on metrics of constant scalar curvature r equals minus 2. And that's a finite dimensional moduli space equivalent to the moduli space of Riemann surfaces. So you localize on the locus of this delta function, and then to get the contribution of the delta function, you just have to do a one-loop integral. However, in the work you heard about this morning, it's important that on an orientable surface, JT gravity is not just one loop exact, but tree-level exact, in the sense that the one-loop correction is trivial. In other words, the product of determinants that multiplies the delta functions is actually 1. So everything reduces to computing volumes of moduli spaces, where the volumes are defined by classical formulas with no one-loop correction. So we'll get back to how there can be a correction in a second. Now, in traditional random, I also want to tell you why it's natural to consider time reversal symmetry. So in the traditional random matrix theory of Wigner and others, unitary symmetries are not very important, but time reversal symmetry is important. The reason is the following. Suppose you have a unitary symmetry, for example, a symmetry G whose square is 1. Then you just diagonalize G, so it's 1 in one block and minus 1 in another block. And in a G-invariant theory, the Hamiltonian will be block diagonal on the same basis. And random matrix theory would suggest that the two blocks are independent random matrices. So you just do ordinary random matrix theory as if there were no symmetry, except you do it twice, once in each block. So in that sense, having a symmetry doesn't add much. Time reversal symmetry is different because it acts inside a single block and changes the nature of the block. So there are two T-invariant Dyson ensembles, depending on whether T squared is 1 or minus 1. If you assume that T squared is 1, then the symmetry of an L-dimensional Hilbert space is reduced from UL to OL, and the Hamiltonian becomes a real symmetric matrix. If T squared is minus 1, the symmetry is reduced to a symplectic group, and the Hamiltonian is an antisymmetric tensor of that group. So in all, there are three traditional Dyson ensembles in random matrix theory. There's the one that figured this morning, an L by L Hermitian matrix with unitary symmetry. If you assume time reversal symmetry, then there are two other ensembles, one with orthogonal symmetry, one with symplectic symmetry. In each case, the Hamiltonian is considered as a random matrix with the distribution of this form with a suitable function f. Where if you're only interested in short-range correlations among eigenfunctions, the precise function f doesn't matter very much, so Wigner, Dyson, and Maytag generally assumed a Gaussian function. F was quadratic. So in nuclear physics, there is time reversal symmetry. So the ensemble important in nuclear physics is the second one. Now, each of the three ensembles can be related to two-dimensional geometry by expanding the path integral in perturbation theory and following 't Hooft's construction in which a propagator is taken as a thin ribbon with the initial and final index of the matrix on the edges of the ribbon. The only difference is that for a Hermitian matrix you get orientable two manifolds only, but in the other cases you get unorientable two manifolds. So that's because for the T-invariant ensembles, the propagator has a twisted term. So writing Hij and HKL for matrix elements of the Hamiltonian H, the two-point function of the matrix element of H for one of the T-invariant ensembles looks like that, with a plus or minus sign, depending on whether the symmetry is orthogonal or symplectic. Whereas for a unitary symmetry, we have only the first term, no second term. So if you make a one-loop diagram where you have a scalar particle representing the propagation of the matrix running around in a loop, then 't Hooft tells you to turn the loop into a thin ribbon, but the ribbon is either twisted or untwisted when you go around. So in one case, the ribbon is an annulus, the other one is a Bogian strip, familiar worldsheets in open string theory. If you want to follow 't Hooft and make a two-manifold by gluing in a disk to each index loop, on the left there are two index loops, so you glue in two disks, one inside and one outside. But on the right, since it's a Bogian strip, there's one boundary, you glue in only one disk. So on the left you get an orientable surface of Euler characteristic 2, which is a two-sphere. On the right you get a surface of Euler characteristic 1, which is a copy of RP2, or a cross-cap, this is often called informally. So the Euler characteristic is just the number of, in general, is just the number of disks that you glue in. So it's 2 or 1 in these two cases. So here you get a factor of L for each of two index loops, L squared. Here you get a single factor of L. So RP2 is of some leading in the 1 over L expansion. It's order L instead of L squared. Now, the twisted diagram will get a plus or minus sign because of the sign in the propagator. So you learn that the contribution of a 2 geometry with the topology of RP2 to the path integral has a sign that's different for the two Dyson ensembles. So you learn, at least in this example, that the two Dyson ensembles differ by whether, in the sum of the two geometries, you should weight a cross-cap with a minus sign. And that's actually true to all orders. And the T-invariant ensembles were related to orientable two geometries in early papers. So if you're familiar with what happens with orthogonal and symplectic Chan-Paton factors, surprising. So, orthogonal and symplectic symmetry for open strings has to do with the sign of the orientable operation, the exchange of the twins of the string. So it goes into the sign of the Mobius strip amplitude. So, orthogonal and symplectic symmetry have to do in open string theory with the sign of this amplitude, analogously to what I've told you in the context of the matrix model. So, to do JT gravity with time reversal symmetry, we'd like to compare JT gravity on a possibly unorientable surface to the T-invariant Dyson ensembles with orthogonal or symplectic symmetry. Now, here we run into the following fact. On an unorientable two-manifold, JT gravity is still one-loop exact, because the integral over phi always gives a delta function corresponding to one-loop exactness, but it's no longer tree-level exact. So on an unorientable spacetime, you have to calculate a one-loop correction. And the methods involved in computing it are interesting, and could have certainly filled this lecture, but today I'll just state what the answer is. So, first of all, I'll say it in an orientable case and then compare it to the unorientable case. So, solutions of JT gravity are hyperbolic surfaces